The whole idea of Hess's law is the fact that energy changes that occur in a reaction are independent of pathway. That if we look up here at the reactants CH4 and 2O2, it doesn't matter if we do the reaction in a single step, as is done on the left-hand side here. Okay, so this might be one step, or two steps over here on the right, where you first make this water in the gas state, and then you cool it down to water in the liquid state. No matter which way you do it, you're always going to get the same transfer of energy. Okay, that's what's at the core of doing these Hess's law problems. Now, a couple of things that you want to make sure that you take away when you think about doing these problems. If I'm going to run a reaction in reverse, let's say that I wanted to go from the CO2 and H2O down here back up to that. So run the reaction the opposite way. Well, when we ran it forward, maybe we'll call it delta H of the forward reaction. So I'll put a big F down there. That was minus 890 kilojoules. What would you expect to happen if we ran it backwards? So maybe let's call it delta H B for backward. Well, as you probably guessed, that would be positive 890 kilojoules. In other words, if I end up releasing 890 kilojoules when I run the forward reaction, if I try to do it in reverse, then I'm going to have to absorb or take in 890 kilojoules. Another way to say it would be that if the forward reaction is exothermic, then the reverse reaction is going to be endothermic. Okay? So there's one more thing I want to talk about in terms of doing this calculation of delta H, right? That's the Hess's law. We want to know that delta H for the overall reaction. We've talked about what would happen if we ran a reaction in reverse. Let's look at one more idea on the next slide, and then we can put it all together on the third one. All right, remember again, we're using Hess's law, the idea that it doesn't matter how we go from the reactants to the products, okay? The energy change will always be the same. We're going to use the idea of Hess's law and a series of chemical equations to calculate delta H. Okay, so along with standard enthalpy of formation, we could use that to calculate delta H. We can also use Hess's law to calculate delta H. There's one more way to calculate delta H, calorimetry, which we'll talk about in a little later on in class. Okay, so let's talk a little bit more about one other adjustment that we can do. If we were to run this whole reaction twice, it probably wouldn't surprise you that we would get 2 times the energy released. Okay, so if we look at the initial, and I'm going to leave out the physical states here. If we take one methane and react it with 2O2 to get CO2 and 2H2O, we know that if we just do that reaction once, the delta H is negative, sorry I'm running out of space here, 890 kilojoules, so I can't quite fit that in there. However, let's say that you ran it a second time. Well, it probably wouldn't surprise you that you get another 890 kilojoules. So if we take and we double the quantities, so instead of 1 CH4, we do 2 CH4s. Okay? Instead of 2 O2s, we do 4 O2s. In other words, we're multiplying everything by 2. Rather than 1 CO2, we get 2 CO2s produced. Rather than 2 waters, 4 waters. Well, question is, if I multiplied everything in the reaction by 2, what would happen to delta H? Well, it probably isn't shocking to realize that we would also double delta H. So if we do 2 times negative 890 kilojoules, we will get negative 1780 kilojoules. Okay, so in the last slide we talked about the fact that if you reverse a reaction, you have to change the sign for delta H. Here what we're doing, if we double the reaction, you also have to double delta H. Right? You may be asking yourself, well, okay, that all makes sense, it all seems logical. How do we use this, or how does it sort of show up in a problem or in a strategy for solving a problem? So let's look at that on the next slide. All right, so here's a typical Hess's Law type problem. The first part up here is what we want to look at. Okay, it says using the following standard enthalpy of reaction data. Okay, so here's all the data right here. Calculate the heat of reaction for the combustion of ethane. Okay, and they're nice enough to give us the balanced equation right here. Okay, so as we've been talking through these slides, we're trying to figure out delta H. Okay, how much energy is transferred by doing this reaction as written. Okay, that's the important part. We got to get things as written. So we want to use our reactions up here that the data that we had before. Let's start with the first equation. Okay, in this first equation, you can see that that's where ethane appears, and we can see down here in our target equation, if you want to call it that, that we have two ethanes, okay, as a reactant. So there's a problem. We need it to be, we need to somehow get ethane to be a reactant, and we need two of them. Okay, so what we need to do in mathematical terms is we need to take this first equation here and we need to reverse it and multiply it by 2. And you can see that they've done that down here. The ethane now appears as a reactant. Okay, so it's a reactant and the other materials are now the product, so it's been reversed. And they're multiplying the reaction by 2. And of course that means they ultimately have to change the sign of their delta H and multiply it by 2, which they did. Okay, and again, that enabled us to get the two ethanes as a reactant. All right, the next thing they did is they chose to move on to CO2, okay, rather than O2, because O2 appears actually in 2 of the equations. That's right here. Okay, so they said, all right, well, we need 4 CO2s produced as a product. Well, in the second equation here, CO2 is a product, but only one of them. So we have to multiply the entire equation by 4. And they did that right here. Okay? They took the whole equation, multiplied it by 4, and of course that means they have to subsequently take the delta H and multiply it by 4. Okay? The last thing they need in their target equation is 6 waters. Well, water appears here, but as in the problem with CO2, there's only 1 water, and we need 6. So they're going to take this whole equation and multiply it by 6. So that's what they did right here. Okay, whole thing's multiplied by 6, including the delta H. All right, so they've now matched up and gotten everything that they need for their target equation. We have the 2 C6H6 in the right slot right there. Okay, we have 4 CO2s and 6 H2Os. Okay, so again, they're going to get the 4 CO2s here and the 6 H2Os from there after they finish doing the multiplication. Then they copy down the rewritten equations. All here. Here's the first one, second one, third one, with all of the adjustments made. So you may be asking yourself, well, why didn't they do anything with oxygen? Well, I think it's going to turn out that oxygen, we're going to end up with the right amount of oxygen. They didn't have to worry about that. Okay, you see a lot of lines through materials. Okay, so like here's a line through the 4C that was produced in the first reaction. If you have something on both the product side and then in a subsequent equation it's on the reactant side, you can cancel them out. So 4C's up here, cancel out the 4C's down there. The 6 H2's up here are canceled by the 6 H2's down here. okay? And nothing else cancels. You can also see that we end up with a total of 7 O2s, and when everything is copied down, there it is appeared, okay? To get the delta H in the end, you just have to add up all of these values, and you've got delta H for the equation. So once we figure out delta H, it's minus 3,123 kilojoules. All right. So in theory now you know that delta H can be found two ways. Okay. You can find it by doing the standard enthalpies of formation using the table of values, or you can use a series of thermochemical equations and the concepts from Hess's Law to calculate delta H. And as I said, there's one more coming up that we'll look at.